Okay, so time to start. Uh, if you have any questions, feel free to ask me. So you can ask me after the lecture, or you can send me emails, or you can make appointments. Whatever way you can contact me, let me know. Let me know your questions. Um, so we are halfway in the topic about interest rate, about this money and personal finance, right? So today we are going to continue. So we'll have one more example of investment, but that example is a little bit artificial. Our real target is mathematics behind it. I think the mathematics behind it is more interesting. So we'll have one more example, and after that, in the previous lecture and also in today's lecture, we quote some mathematical facts. Right? We didn't explain them. So now I want to use the second half of today's lecture to explain all these mathematical facts. Okay, so that's the plan. Okay. Now, what is going on? Okay, so let's do a quick recap. When we talk about interest, there are two ways, right? One is simple interest. The other one is compound. But we have mentioned in real life, almost all interest rates are calculated are compound. We seldom use simple interest rate. Okay, so if you so the main tool we had last time is this proposition. So let me read it one more time. So if you invest C0 dollars with an annual compound interest rate of alpha, then you will have C sub n, which is the dollar you have after n years, C sub n equal bracket 1 plus alpha to the power of n times C0. Right? This is the formula we use over and over again. And also, last time we have we have seen that there are four parameters inside this equation: C0, Cn, and n and alpha. Right? So lots of problems are given in this way. So maybe we know 3 out of the 4 parameters, and then we have to use this equation to find the last one. Right? So we have seen the variation of this theme many, many times. Okay, so this doesn't work well. Okay, so let's try to recall what we have learned last time. For example, let's work on this easy question together. Okay, if the annual interest rate is 12% and you borrow $1,000 for 6 months, right? How much should you pay? Right? After 6 months, you have to pay the money you borrowed. What is the amount of the payment? Okay, so essentially, we want to calculate the interest rate for 6 months, right? So we know the annual interest rate. In other words, we know the interest rate for 12 months. So we want to know the interest rate for 6 months. Let's call it x, right? So then we have this equation. Why? Because the right-hand side is after a year, what is the payment you should pay? Suppose you borrow it for 1 year, right? So you have yearly interest rate 12%. So after 1 year, you own 1,000 times 1 plus this 0.112. Now suppose you use this 6 months interest rate. So after first 6 months, you own 1,000 times bracket 1 plus x. Now after the second 6 months, you have to multiply the number by 1 plus x again. So that's why you get 1 plus x squared. Right? But this is the same way. They all give you the number of after a year how much you own. Right? So they are equal. So by this equation, we can solve x. Right? So So it's very easy to solve x. You just punch your calculator, you get this this figure, 5.83%, and then you should pay using 1,000 times bracket 1 plus this 5.83%. Then you get the number, which is this. Okay. We have mentioned this fact before, so it is not you cannot get x by simply dividing things by 2. It's not correct. You have to use this formula. Okay? So I hope this reminds you what we have done last time. Now here is the main example of today. Right? So so the scenario is this. So you have certain amount, say $C, then you ask some bank, right, say DBS, right, some bank to invest in some shares over a certain period, let's say n months. Okay. Now after n months, you will get a certain number of shares of the bank. Okay, say X, capital X. Okay. Maybe I should stand over there. Okay, so sorry, I have to read it from this screen. Otherwise, so since the price of share goes up and down, so DBS give you two options, right? So option 1 is we calculate the average price of one share. Let's say the average price is P bar over the period. Then you get C divided by P bar many shares, right? So this is option 1. You calculate the average price of the whole period, and then C divided by that number will give you the number of shares. So this is option 1. So option 2 is you don't take the average. Every month you divide C evenly to C over N, right? And then every month you spend C over N C over N dollars to buy shares based on the price of the month, right? So then in the end you take the sum. Okay, so this is option 2. Now the problem is, okay, which one is good for you, is better for you, right? Which option should you choose? As I said before, actually, I care more about the mathematics than the example. Okay. Okay. So first, let's turn this problem into mathematical problems. Right? Do it step by step. So first, let's fix some notations. Let P sub k be the price of one share at the month k, right? So, and P bar is the average price of one share over the whole period, n months, right? So, in other words, P bar is the average, right? You add P1, P2, all the way to Pn divided by n. So, this is the average of the price. Now, under the scenario we set, in option 1, you get x sub 1, which is C divided by P bar. This part we already know. Right? mean shares. Now, in option 2, you get this amount. So x sub 2, C over N. So this is each month you will spend this amount to buy share. So for the first month, you get this amount divided by the month, the price for the first month, which is P1. The second month, you use the same amount but divided by that, the month of that, the price of that month. So C over N divided by P2, right? So all the way to the nth month. So in the end, you get C over N times this notation I introduced last time. So this is the sum, which is the sum from I from 1 to N, 1 over Pi. In other words, it's 1 over P1 plus 1 over P2 plus dot 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 1 over Pn. Right? So this is option 1, this is option 2. Okay, so quite easy. So the question is, which is greater, x1 or x2? Okay. Are there any shortcuts? Right. Okay, I'm going to give you some solution, but what is your intuition? Yeah, put in some numbers. Okay, so that's a good idea. And also you can try extreme cases, right? So sometimes it's hard to do something in general, but you try something extreme. So let's just try. Suppose at certain months, the price was extremely high. It's like infinity. It goes through the ceiling. Okay. Just imagine maybe at the PN, the last month, the price was like, I don't know, it's just extremely high. Now, the P bar will be extremely high. Right? If this guy is infinity, then the whole average thing is still infinity, almost infinity. Now, in scenario 1, you'll get almost nothing because the P bar was so high that you don't get anything almost, right? So in option 1, in that extreme case, you don't get much, okay? Now, how about option 2? Now, suppose the PN was so big that this month you get almost nothing, right? 1 over PN is like 0. So therefore, at the nth month, you get almost nothing. But at the other months, right, so maybe the price was more reasonable, you'll still get something, right? So by looking at this extreme case, it seems that option 2, at least in this extreme case, option 2 is better, right? Because the reason I just said. Okay, but we are going to give a rigorous mathematical argument to convince you that option 2 is never get worse than option 1. Okay, so let's unravel the question. So we want to compare x sub 1 and x sub 2. So x sub 1 is this, C divided by P bar, which is this. X sub 2 is, I copied down the numbers here. So we compare these two, right? Now you can cancel the C without any problem and flip the thing, right? The fraction. So this term become n over P1 plus dot 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 plus Pn. Now this term is the same, just cancel the C. So you compare these two, okay? Now this is the same as, imagine you have an inequality or you have an equality here. You can cross multiply, right? Because every number involved are positive. So there's no danger of flipping there's no negative numbers. So there's no danger of flipping the inequality. So imagine the end is either less than or bigger than or equal. Then you can always cross multiply. So comparing these two terms is just like comparing n squared with the product of these two, the P1 plus dot 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 plus Pn times 1 over P1 plus dot 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 1 over Pn. Okay, so we want to compare these two. So I want to show you that n squared is always less than or equal to the right hand side. So in other words, option 2 is never getting worse than option 1. Okay. Is the working okay? Right. Okay, so now how do you show this? This is this is hard. Right? Now, surprisingly, we are going to make use of some easy fact, some fact about quadratic equations. These you learn from JC or from elementary school. Okay, so let's recall some basic knowledge on quadratic. Quadratic means degree 2 polynomials. So the quadratic polynomial is of the form f of x equal ax squared plus bx plus c, where a, b, c are numbers, x is the unknown, right? So this is a quadratic polynomial. Now we can find its roots, right? So if set equals 0, then you look at its root in real numbers. We don't count complex numbers. So in real numbers, so you know the formula. So there are two. Okay, sometimes there are two roots, which are given by this formula, right? So this the root is equal to this fraction. Okay. Now inside this expression, this b squared minus 4ac is called discriminant, right? So when this guy is bigger than 0, the polynomial has two roots. When it is equal to 0, it has exactly one root. When this guy is less than 0, it has no root, right? So in picture, so I copy this from internet. It's an ugly picture. So it should be a parabola, but somehow it's like a circle or something. So the typical example of no root is like this. So for example, f of x, let's say, f of x equal x squared plus 1. So the whole curve is hovering above x-axis. So there's no intersection. Therefore, there's no root, right? Now the case it has exactly one root means it somehow just meet the x at here. So in this case, you would have exactly one root. Now usually you would have two roots like this. So in this case, the typical example, for example, is x squared minus 4. So you have two roots plus minus 2, right? So these are the typical examples. Okay, so now the fact we are going to use is this. So the first two cases happen precisely when fx is bigger than or equal to 0 for any x, right? So in this curve, the whole green thing is bigger than x. The value is the green value is all above x. In the second case here, there's only one 0 value, which is this 2, 0. Otherwise, it's all above 0, right? So the first two cases happen precisely when the curve is above x-axis. And this holds precisely when b squared minus 4ac is less than or equal to 0, right? Corresponding to the last two cases. Okay? Now, okay. You may wonder why I mentioned quadratic equation, right? So here is to me it's like magic, right? So it's like consider this expression. Well, for those of you who have taken some math courses, like you are from SOC, if you see a proof or a calculation begin with consider something, it's usually something very smart, right? Because this may not be the thing you consider, right? When you work on this problem, you compare two numbers, and then why should I consider this? Right? So usually you need some hard work, or you need some smartness to consider this. But well, the textbook or the lecture notes or someone else did it for us. So let's follow his idea. Let's consider this expression. See how we can make use of this expression, right? So the expression, so I consider this f of x. F of x is a sum of bunch of squares, right? So this is a summation symbol. Is I from 1 to n, x times square root of pi plus 1 over square root pi. And this thing, the whole thing squared. Right? It's a very clever choice of the f of x. So that's why I label it like a magic. So let's just follow the solution. So f of x, let's consider this f of x, which is the sum of the squares. Okay. Now, so the observation is f of x is always bigger than or equal to 0. The reason is the right-hand side is the sum of some squares. As you know, for any real number, the square is non-negative, right? If you square even -1, you get 1. So a square of a real number is never negative, right? So each single square is bigger than or equal to 0. You add n terms of this is still bigger than or equal to 0, right? So the first observation is this expression, no matter what x you choose, is always bigger than or equal to 0. Okay? Now, on the other hand, this f of x is of degree 2, right? So we can actually calculate what f of x is, right? So here, I'll try this, whether I can mark something on screen. Okay, so if you expand the square, right, you'll get this term, right? So you know that a plus b squared is a squared plus 2ab plus b squared. Now think of a is x times square root pi. When you square this term, you get this pi times x squared. If you square the last term, you get 1 over pi. And then the 2ab corresponding to 2 times this and that. Right? So you expand the square, you get this. Next, here you need some experience on how to handle this sigma. So the sigma is like a sum. So sigma is lots of addition, right? But inside the bracket is also addition. Addition and addition, you can change the order. Right? It doesn't matter how you add them. So therefore, you can sort of put this addition. Okay, so you can calculate this sum first, and then you calculate the second sum, which is I cancel this, right? So this is 2x, right? The sum of 2x. So what is this? So this is the sum of 2x times okay. So what is this? So remember, this is a sum from I equal 1 to n, a sub I. So when I equal 1, I have 2x. And then when I equal 2, I also have 2x. And all the way to when I equal n, right? So I have n copies of 2x. So if I add them, I'll get 2n times x. Right? That's why we have this term. Okay. So the last term is easy. So you just put this sum with this 1 over pi. Is that okay? So this is a manipulation of the summation symbol. If you are not comfortable with this, try to expand and then reorganize the terms, you get the same thing. Okay. But it's pretty easy to manipulate. It's just it takes a few trial and error. You know how to manipulate the sum. Okay, so in short, this f of x is indeed in quadratic form, right? So it is something times x squared plus something times x plus some constant, some number. Okay, so we are here. We are at this. So now we have two observations. One is fx is always bigger than or equal to 0. The second observation is this guy actually is a quadratic. Now by the previous slide, we know that this guy, the discriminant, has to be less than or equal to 0. Right? So b squared minus 4ac has to be less than or equal to 0. So let's see. So in this case, what is the capital A? Capital A is a coefficient of x squared. So this is a sum of pi. B is just 2n. C is a sum of 1 over pi. Right? So these are the ABC. Now what is b squared minus 4ac? So b squared is 4 times n squared. Right? 4ac is 4 times the product of these. But 4 and 4 cancel. So therefore you get n squared minus this product is less than or equal to 0. So you move n squared to the other side, you get this. So n squared is less than or equal to this product. So that's the conclusion is the option 2 is better than option 1. Okay, so I guess as I said, the interesting part is the mathematics, right? So we probably use that example as a vehicle to convey this message. Now I want to take another look. So this is another proof of this inequality. But the proof actually is more powerful. So the proof, this proof talk about arithmetic means, geometric means, and something called harmonic means. So these inequalities are more common in mathematics. So if you study math, maybe even in JC, you may encounter these inequalities. So I want to show a funny inequality like this. Then from this funny inequality, it's very easy to see our inequality, right? So let me say it again. So I want to present another proof of the inequality, n squared less than or equal to the product. Okay. So instead of directly attack this, I want to show something more general. So the more general thing is this claim. The claim is for any integer n bigger than or equal to 2 and any real numbers p1 dot 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 pn which are positive, because I will talk about square roots or I'll talk about 1 over pn. So I cannot allow these things equal 0. I cannot allow it negative. Otherwise, it doesn't make sense. Right? So let's assume I have positive real numbers, p1 dot pn. So the conclusion is this term, n over 1, so I don't read. So n over this sum is less than or equal to the nth root of the product. And this is less than or equal to, this term in turn is less than or equal to the average, the p1 plus all the way to pn divided by n. Right. So I want to show this inequality. Now, why this claim implies the inequality I want? Well, if you just look at this term and cross multiply, you get n squared here, you get the funny product on the right hand side. So therefore, n squared is less than or equal to the funny product, right? So it boils down to showing this claim. Okay. So there are names for these three terms. I think probably you have heard of this. This is the average is called the arithmetic mean. Then this is called geometric mean. And then this term also have a name called harmonic mean. Okay. So, okay, so the claim was pretty abstract, right? So it's actually a family of statements. So for each n, you have one inequality. So let's look at them one by one. So for example, when n equals 2, we only have two numbers, p1 and p2. So the arithmetic mean, I'll shorthand write it as am, right? Arithmetic mean, am, is p1 plus p2 divided by 2, right? Now the geometric mean is the product, p1 times p2, then take nth root, take a square root. Now n is 2, so take square root. So the harmonic mean is 2 over this 1 over p1 plus 1 over p2, right? So in this case, when n equals 2, the inequality becomes this is a harmonic mean is less than or equal to square root of p1, p2 is less than or equal to p1 plus p2 divided by 2. Right? So this is the claim when n equal 2. When n equals 3, we have three numbers, p1, p2, p3, right? So now the arithmetic mean is you add them together divided by 3, right? The geometric mean is you multiply the three terms together, but this time you have to take cubic root, right? So you have to take cubic root here. The harmonic mean is like that, right? So I guess the arithmetic mean and geometric mean are more popular than this harmonic mean. So in the old days, for example, in ancient Greek, they do not have the concept of real numbers, or even for zero or negative number was developed quite late. So people think of these equations in terms of geometry, in terms of the length of a segment or area of something. Okay, so now I want to say how I want to find the geometric representation of the geometric mean, right? For example, let h denote the square root of p times q. Can we somehow see what h is, right? So I claim that all you need to do is this: you draw a right angle triangle like this, and then the red segment is equal to h. So I'm trying to say that in this picture, h squared is p times q. Okay. Yes, actually, if you know a little bit Euclidean geometry, you have other proofs. For example, you can draw a circle here, and then you can extend h symmetrically to the other side. Then there's a theorem saying if you have two chord, right, cross like this, then h times h will be p times q. Right? So there are lots of other proofs. But if you don't know that, you can use Pythagorean theorem, which says, you look at this right angle triangle, so you know that the r squared plus s squared is the square of this side, right? So you see that r squared plus s squared is bracket p plus q squared. So you can expand like this, right? Now if you look at r squared and s squared in the other way, because this is also, for example, here is also a right-angled triangle. So r squared is p squared plus h squared, right? Now, similarly, look at this triangle. You get s squared equal h squared plus q squared. So you write the same number, r squared plus s squared, in two ways. If you compare the two terms, immediately you get h squared equal pq. Right? So this is in old days, people see things through geometry. So that's the geometric way to express geometric mean. Okay, so now I want to prove, I want to justify this, right? I put the word optional here because this is a general education module, so all proofs are not required. But I'm teaching mathematics, so I like to teach proofs. I like to give you reasons, right? So this part, it will not be tested, but so it's optional. Okay, but it's nice to know, so that you know the reason why something is true. Okay, so let me make an attempt to convince you that there's a rigorous way to justify the family of claims about AM and GM. Okay, so let's just go through this. So first we only focus on one inequality because the other side follows quite easily from this. You'll see an example. So now how do I show the geometric mean is less or equal to arithmetic mean? So we do this funny, we have 3 steps. Usually, if you have a family of statement, you use something called mathematical induction. But in this particular case, mathematical induction does not apply in a simplest form. So you have to play some trick. So the trick you play is this. Okay. So first we show that the statement is true for n equal 2. And then you show that for any power of 2, so you just iterate the proof. It's very easy to get for any power of 2, the statement is true. So you get an infinite family, but you have lots of gaps in between. Sorry. Let me try to say this. So here is a number line, 2, 3, 4, 5, 6, 7, 8, okay, say 9, ... right? So I want to show that, so this is my n. So I want to show for every n, the statement is true. Okay, so can I change color? Is this the... Okay, so I first check n equal 2. So I take this number. Okay, and then somehow I will, you'll see very easily, I'll repeat the proof for n equal 2. I get all the power of 2. So from n equal 2, I jump to n equal 4. And then from n equal 4, I double. I jump to n equal 8. 4, 8. And then I get n equal 16. So I'll get lots of more numbers are true. But at the same time, I leave lots of gaps in between. Right? For example, 3, I didn't show. I jump over. And these numbers, 5, 6, 7, I jump over. And here I jump over even more numbers. So the second step is I will show all the power of 2, the statement is true. Right? And then the last step is I will fill out the gaps by going from 4 to 3, I'm going from 8 to 7, 7 to 6. So I'll go these things backwards. Then by doing this, I fill out all the gaps. Right? So this is the plan. This is quite complicated. So let me repeat. Start from n equal 2. And then I do it for all these powers of 2. And then I fill out the gaps. Okay, so that's the approach. Now n equal 2 actually is the most interesting. Probably have seen this. So we have to use the property of any real number square is bigger than or equal to 0. Right, now this guy, square root of p1 minus square root of p2 is a real number, so the square is non-negative, right? It's always bigger than or equal to 0. So then you expand the square, you get the right-hand side is like this. And then you move things around, you move this negative 2 times square root p1 times p2 to the left-hand side, and then divide by 2, you get this, right? Quite easily, just 3 lines. So you get for n equal 2, the GM is less than or equal to AM. Okay? And then let's get 4. So, sorry. Before I get to 4, I want to say the harmonic mean less than or equal to geometric mean follows from this. Why? Because this inequality holds for every number, right? So it doesn't matter what P1 is, what P2 is. So I can substitute 1 over P1. So this inequality works for every real number. So I can consider my let's say P1 is 1 over Q1. My P2 is 1 over Q2. Now what do I have? I get square root of 1 over Q1 times 1 over Q2 is less than or equal to 1 over Q1 plus 1 over Q2 divided by 2. Right? So, but it doesn't matter I call it P or Q. Right? So this is true for every Q1, Q2. So now I write it as P1, change Q back to P. Right? So I get this. I get 1 over P1 times 1 over P2. The geometric mean of these two numbers is less than or equal to the arithmetic mean of these two numbers. Right? So I have this. But you flip over, then inequality change. Because when you flip the denominator and numerator, the inequality change. So therefore you get square root of P1, P2 is bigger than or equal to this guy. So that's the geometric mean is bigger than or equal to harmonic mean. Right? So the same argument holds for arbitrary n. You try it for arbitrary n, it gives you the same thing. So therefore, I will not bother to show the harmonic mean less than geometric mean. I just show this, geometric mean less than arithmetic mean. Okay, so now we can talk about n equal 4. So again, we use the n equal 2 case. So you see so we know that square root of Q1 times Q2 is less than or equal to Q1 plus Q2 divided by 2, right? So now let Q1 equal square root of P1, P2, Q2 equal square root of P3, P4. What do I have? So the left-hand side, square root of Q1, Q2 is this, right? Because Q1 is that, Q2 is that. So the left-hand side is square root of square root. So the nested square root is like this. It's less than or equal to. Now, inside this square root, I use the geometric mean of P1, P2 is less than or equal to P1 plus P2 over 2, right? So this circle term is less than or equal to this square term. This is a n equal 2 case. Similarly, the second circle term is less than or equal to the second square term. So I get that. Okay. Now for this, it's still of the form square root of a product, right? So this is still in a form of geometric mean. So it should be less than or equal to arithmetic mean. So it is less than or equal to the first number, the first square plus second square divided by 2. Right? So I get this. But this is exactly right. So this is the fourth root because I have nested. I take square root one time and second time, so I get a fourth root of the product. Is less than or equal to, if you massage this term, you get P1 plus P2 plus P3 plus P. The sum of the four numbers divided by 4. Right? So that's the way we go from 2 to 4. Now here you can try it. The same method applied to you can go from 4 to 8, then you can go from 8 to 16. And it's the same reason. You just apply this. You just apply the n equal 2 over and over again. Okay, so that's the way we get all the power of 2s. Now, how about this backwards? How about the numbers in the gap? We just look at one example, right? The general argument is similar. Okay. So let's go from 4 to 3 as a typical example from k to k minus 1. Okay, so let's try. So I want to go from 4 to 3, right? So I know this formula, gm less than or equal to am, holds for n equal 4. So I consider the four numbers, let's say q1, which is p1. I consider q2, which is p2, q3, which is p3. But I choose my q4 to be the average of p1, p2, p3. So I choose this. So by the n equal 4 case, I know the geometric mean of q1, q2, q3, q4 is less than or equal to the arithmetic mean of q1, q2, q3, and q4. So the right-hand side is indeed the arithmetic mean of these four numbers, right? So this is q1 plus q2 plus q3 plus q4, then divided by 4, right? So this is the inequality of n equal 4. Now from this, I want to do some I want to do some calculation. So you know that taking the fourth root is like raise the power of 1 over 4, right? So you have this term p1 times p2 times p3 bracket to the 1 over 4. Now this guy also I can write it as the arithmetic mean of the three numbers to the power 1 over 4. Right? 1 over 4, raise it to the fraction power is like taking the roots. Okay. And on this side, just do a little bit arithmetic. So this is 3 over 3. All right. So this is 1 times bracket p1 plus p2 plus p3. So you get 3 over 3 plus 1 over 3. So you get 4 over 3. why don't I just write it? Right. So this side, this is equal to 3 times 4 P1 plus P2 plus P3, and then divided by 4, right? So you get P1 plus, so the 4 and 4 cancel, so you get P1 plus P2 plus P3 divided by 3. Okay, so you get this. So then what? Then you divide this power. You divide P1 plus P2 plus P3 divided by 3 to the power 1/4. What is left is 3/4, right? So this side you have originally have power 1, but you canceled 1/4, so it remains 3/4. So you get this, right? But just manipulate the power, right? Raise it to the power 4 and take the cubic root. You get the inequality like this, right? So this is a way to go from 4 to 3, right? So you can try the same thing. You can go from k to k minus 1 in the same fashion. So therefore, you can fill out the gaps by backwards induction. Okay. How many of you have seen this before? Good. So if this is the first time you have seen it, it's a little bit complicated. But some of you who maybe you have gone through some training of I don't know, some competition, then this is a typical inequality. It's so you don't need to know the proof. It's optional, but I think it's nice to see it. Okay, so that's the maybe the first half. Any questions? Okay, so do you want to take a break, or let's continue and finish early? Which way? Break? Okay, let's take a break. Okay, so let's continue. Now I'm going to pay back my debt. Right? I mentioned a few mathematical facts. Now I'm trying to give you reasons. Okay, so the first fact is this: is we are talking about something called arithmetic progression. This probably you have seen in high school. Okay, so the definition says, suppose you have a sequence of numbers, and then it is of this form. The difference between two consecutive terms are always the same, right? For example, the difference here is d. Now, if you look at the second term and third term, you take difference, it's still d, right? So arithmetic progression is a sequence like this, okay? So this a is called the first term, and each number is by you can view it as you add a fixed number d to each term, then you get the progression, okay? So the d is called a common difference, right? Because you take two consecutive terms, the difference is exactly d. So now, for example, 100, 105, 110, 115. So the difference is always 5. So this is an example of arithmetic progression. Now we are interested in what is the sum of n terms in arithmetic progression. So some people call it arithmetic series. Right? So we are interested in adding the first terms, right? So here I change from 1 to n, so the first n terms. Now, sometimes you can start from n equals 0. You can start from I equals 0. So the first n terms, if you start from 0, the last term become n minus 1, right? Here you go from 1 to n. Now suppose you all shift by 1. You start from 0, you end up with n minus 1. So sometimes this is confusing, but if you understand what you are doing, it's not that bad. Okay. So this is the sum of first n terms. Okay. This is okay. So the typical example is this so-called triangular numbers, right? So T1 is just one dot. T2 is, that's why it's called triangular. Right? It's like triangle. So it's 1 plus 2, right? 1 dot plus 2 dots. T3 is 1 dot plus 2 dots plus 3 dots. T4 is 1 plus 2 plus 3 plus 4. Right? So the obviously 1, 2, 3, 4 goes in arithmetic progression. So the triangular number is the sum of the arithmetic progression. Right? So is there a formula? Is there a closed term for the triangular number? So the claim is Tn is 1 plus 2 plus 3. So this is the definition. Tn is this. The claim is you can find a closed term which is half of n times n plus 1. Okay. Now the proof. So the proof goes like this. It's quite easy. So Tn is the sum. So I write Tn in this way. Now I write Tn one more time, but this time I write it in the reverse order. I write n first, then go to n minus 1, and all the way to 2 to 1. So I write the sum in the usual order, and then I write the sum in the reverse order. But they are the same sum, right? Now you add the term up. The left-hand side is 2 times Tn. Now 1 plus n give you n plus 1. 2 plus n minus 1 also give you n plus 1. So if you look at these things vertically, each pair add up to n plus 1. So how many terms do you have? You have n terms. So therefore, the right-hand side, after you add them, you get n copy of n plus 1. So you get n times n plus 1. Now divided by 2, so you get this, Tn equal n times n plus 1 divided by 2. So now there's a famous story about this mathematician. Right? Gauss is supposedly one of the greatest mathematicians ever, right? So it says when he was young, I don't know, so there's a story. So when he was in elementary school, the teacher asked the students to add from 1 to 100, right? Then Gauss immediately get the answer. So the way, so in other words, we want to find T100, right? The triangular number of 100. So what Gauss did is exactly like the proof of the theorem we just shown. So you write the sum in the usual order like this, and then you write it backwards, right? So you add from 1 to 2 to 3 all the way to 100, then you do it backwards. You go from 100 to 99, 98, and all the way back to 1. Now you add them vertically. They always give you, each pair always give you 101. Now you have 50 of these pairs, so it's, the result is 50 times 101, so you get 5,050. Right. So, well, to NUS student, this doesn't mean anything, right? But for elementary school, I mean, in the 1700s, so it shows Gauss was extremely talented. Okay, so more generally, suppose I want to find the sum of first n terms of this arithmetic progression. I want to add these things up. What is the formula? We use the same trick, right? So the claim is equal to this funny fraction. Well, I won't read the fraction. So you know the proof, right? So we want to find the sum. Let's let A sub n denote the sum. The method was you write an in usual order, like this. Then you write an one more time, but in reverse order. Right? So you get that. So you add the two together. The first term gives you 2a plus n minus 1 times d. The second term, second pair, when you add them, give you the same thing, right? Altogether, you have n terms. So the right-hand side is n times 2a plus bracket n minus 1 times d, right? So then you divide by 2, you get this. You get the result. Okay, so it's quite easy. Now, there are lots of examples of these. So one is, what is the sum of odd numbers? The first n odd numbers. 1 plus 3 plus 5 plus dot 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 plus 2n minus 1. Now the answer is n squared. You can try. You can plug in the plug in the data in the theorem, and then you get n squared. But for this particular sum, there is a geometric proof. So 1 is 1 dot, 3 is these 3 dots, 5 is this part. There are 5 dots here. Now in general, for the nth row and nth column and nth row, so you have n plus n, but 1 overlap, so subtract 1. So you have 2n minus 1. Right? So if you add all these dots, it's a square. It's n squared. Right? So this is this picture, again, in the old Greek times, they know how to add these numbers in this way. Now, one more example is you can add these things like that, right? 1 plus 4 plus 7 plus dot dot dot, and then by apply the theorem, you get this result. Right? So I will not explain this. Now, in the textbook, there are other examples of adding things up. So, for example, we have this example. We draw n lines on the plane. So this will form a number of mutually non-overlapping regions, right? For example, if you slash the screen like this, you have two regions, right? Upper region, lower region. Now, if you slash it this way, you get four regions, right? So the question is, what is the maximum number of such regions that can be formed? Okay. So let's look at examples, right? So when n equals 0, there's no slash, no line. It's just one piece, right? It's when n equals 0 is 1. When n equals 1, this picture, if you slash this way, you get two regions, right? When n equals 2, you do this, you get 4, right? When n equals 3, you do this, you get 7, right? And so on and so forth. So the question is, what is, suppose you have n lines, what is the number of regions, maximum number of regions? So the observation is this. Probably in the next slide we'll explain. So I'll read the pattern first. The explanation I'll show you in the next slide. Okay. So the observation is, if you go from 1 to 2, if you go from, let's say, from 0 to 1, you create a new region. If you go from 1 to 2, right, by adding this line, you create two new regions. And then if you do this, you create three new regions, and so on and so forth. So you have to find the number of regions each line created, and then add them up. Okay, so let's see why the number of new regions are following that pattern. So let's see this. Say when you have two lines and you want to add a third line, right? So this new third line intersects all of the existing lines, right? Because you want to have maximum number, right? You don't want to draw a parallel line. The parallel line doesn't create maximum number of regions. So you try to make them cross. Okay. So therefore, suppose you already have two lines, then if you add the third line will intersect the existing lines, right? So therefore, it creates three new regions. Let's show this. So first, it will be stupid to draw a line like this, right? If you draw a parallel line, it doesn't create maximum number. So it's better to draw a line like what he does, right? Something like this, so that the new line cross the two existing lines. Okay. So now, if you draw this, how many new regions do you create? So I don't know, depend on how you count it, right? So this, right? Because on top is still 1, 2, 3, 4, right? Then you create, each intersection will create one more. So you create three new regions. Now here, I don't know. So if you continue, you draw one more, it will intersect the three existing lines. Then it will add four new regions, right? So the reason is like that. Okay, now suppose you have n-1 lines already drawn, dividing the plane into a number of regions that you want to add the nth line. Again, the new line you want the new line intersect all of the existing n-1 lines in n-1 different points. So therefore, it will create n new regions, additional regions. Okay. So in general, for n lines, you get this number, right? So you get these. Because when you draw a new line, you add, okay, originally you have 1. Draw a line, you add 1 more region. Draw another line, you add 2 regions. Draw a third line, you add 3 regions, and so on and so forth. Right? So you want to calculate this number. So which is that, and then this is a triangular number, so you get this. Okay. You have a different way. You can do things in different way to get the recurrence formula and then get the closed term. So I think I'm short of time, so I will not explain this part. Now, once you have arithmetic progression, you have geometric progression. So when we calculate interest rate, we actually calculate the sum of the so-called geometric series. Right? We calculate sum like this. Okay. So now I want to derive a closed term for this. Okay. So let's start from the very beginning. So a sequence of numbers of the form a times r squared dot 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 is called a geometric progression. Right. So instead of adding, you multiply. Right. Therefore, each number is obtained from the preceding by multiplying by the same number, call it r, right? So the r is called common ratio, because if you take 2 consecutive terms, the ratio is always r, right? Okay, so the definition for the sum is you want to add first, if you start from 0, it's very difficult to read this term, because if you start from 0 to n, you have n plus 1 terms. So anyway, so we want to add these terms. We want to find a closed formula for this. Okay, so the claim, which is the mathematical fact 2, right? The claim is if you add, let's say, now I can say first k terms. I start from 0, finish at k minus 1. So the first k terms of this geometric series is equal to this fraction. Okay, I want to say the sum of this geometric progression is equal to this ratio. Okay. Now, so in general, you can add these. This is the formula we use. Okay, so let's prove it. Okay, so how do I? So I want to convince you I can add it up equal to this, the right-hand side. So the proof is that Sn denote the sum. Okay. Just now we add them backwards and we play the trick, right? Now we play a different trick. So we multiply the common ratio r to Sn, right? So left-hand side is r times Sn. What is the right-hand side? Everybody get a copy of r, right? A becomes a times r. A times r becomes a times r squared, and so on and so forth. So the last term, a times r to the power of n, becomes a times r to the power n plus 1. Right? So r times Sn equals this. But if you observe the two equations, there are lots of common terms. So you can take a difference, cancel the common terms. So taking a difference, subtracting, you get r times Sn minus Sn equal, well, all the middle terms are cancelled. AR cancelled. AR square cancelled. The leftovers are this A and the last term here, the A times r to the n. So it's A times r to the n, take away A, subtract A. Okay? And then it's easy to solve, right? Sn will be equal to this formula. Okay. There's a this formula applies when r is not 1. What happens when r equal 1? Can you find? Well, when r equal 1, you don't need this, right? R equal 1 is just a all the way, right? You just n plus 1 times a. Okay, so let's look at this example. So this is called a Hanoi Tower. So it's a game for child, right, to waste their time. So you have 3 poles called ABC. So there are 3 vertical poles, ABC. Now, in this example, you have 5 slabs or 5 discs of different size, and each with a hole in the middle, right? So you put the disc like this, okay? So what is the minimum number of steps needed to transfer all the slabs to this pole? I want to transfer these 5 slabs from A to B. But the condition is at any step, no slab is allowed to rest on top of a smaller slabs in the same pole. So I must put the smaller one on top of the bigger one. I cannot put the bigger one on the smaller one. Okay? Probably you know the game, right? So what we want to know is the minimum number of steps to move things from A to B. Okay. Well, so the solution is find a pattern. Right? We start from 2 slabs and look at 3 slabs and find a pattern, and then we know. Okay, suppose there are only 2 slabs. So how many steps do we need? Okay, so this is pretty easy, right? So you only need 3 steps because I guess I don't need to draw this, right? So you move the smallest one to the 3rd pole C, and then you move there are only 2 slabs, so you move the larger one to B, and then the 3rd step is move the smaller one from C back to B. So 3 steps. Okay. Now let AN denote the minimum number of steps required to move a tower of n slabs, right? So the A2 is 3. Okay. Now can we find a general pattern? So suppose there's n slabs. So let's label them as 1, 2, etc. from top to the bottom. So when can we move the n slab to pole B? So the question is, we have A, we have B, we have C. Right. So here's A, here's B, here's C. So here is the largest slab here. Okay, I don't know how to draw it. Okay. So the question is, what is the moment we can move this to B? To move this to B. Right. So now the observation is, well, you can do this only when the first n-1 form a tower on C, right? Because if you want to do this, the B must be empty. All the rest must be on C. And then it has to be from big to small. So you must have a small tower on C. This is a n-1 tower. This is the last one, right? So this is the observation. Now, right? So this happens exactly when the first n-1 form a tower in pole C. Now, by the assumption to move an n-1 tower, you need this amount of steps, A sub n-1. So it takes A n-1 steps to move the first n-1 slab to pole C. And then it takes 1 step to move the biggest guy from A to B. And then it takes another n-1 steps to move back the n minus 1 steps from C to B, right? So the relation between an and an minus 1 is this. An equal, okay, if you add these, you have 2 copy of an minus 1. The second step take 1 step, so it's 1 plus 2 times an minus 1. Okay? Now, when n equal 5, since we have the formula, we can do it. So a5 is 1 plus 2 times a4. What is a4? a4 is 1 plus 2 times a3. So if you expand, you get this. It's 1 plus 2 squared times a3. What is a3? a3 is 1 plus 2 times a2, and so on and so forth. So each time, the power of 2 increases, right? So in the end, the sum is 1 plus 2 squared plus 2 to the 4, right? So, well, if you use a formula, you get this. You get 31. Okay. So can you figure out the an in general? I guess okay. You are NUS student, right? So you know. Well, okay. So the next fact I want to justify is I mentioned this several times. So the first time I mentioned it is to compare the simple interest rate and compound interest rate. So I was saying exponential growth is much faster. So now I want to give you some evidence. So this I copied from internet. So in computer science, this is a typical table. So if you have algorithm, the number of steps you need is called complexity function. This is a measure of how bad or how good the algorithm is. So here, so the n input is, say, the size is 10, 20, 30, 40, 50, and 60, right? So now suppose it takes, I don't know, these seconds to accomplish operation, right? So the linear time is you take, okay, let's say when n equal 10, you take these seconds. So n equal 20, you double the time, right? N equals 30, you triple, and so on and so forth. Now, how about, suppose the algorithm need square time, right? Suppose it takes n square many steps to finish a job on input n, right? So the number of seconds, you can see that it become much bigger than the first one, right? So it goes like this, but not too much bigger. Now, how about another polynomial? Let's say n to the power of 5. Again, this is getting bigger, right? So when n equal 20, you need a few seconds. When n equal 40, you need a few minutes. When n equals 60, you need 13 minutes. This is much larger than this, right? But however, if you look at exponential, it's extremely large. So when n is small, it's okay. It's not too bad. 2 to the n, when n equal 10, the calculation time is this. N equal 20, well, this guy increase a bit, you need 1 second, right? N to the 5 is worse. It takes more than 3 seconds. N equals 30, well, the exponential is getting worse. It's take almost 18 minutes, right? This guy take 24 seconds. But look at the others. So let's say n equals 50. Now, the polynomial algorithm takes 5 minutes. The exponential algorithm takes 35 years, right? So it's probably longer than your life, right? So now look at n equals 60. The n to the power 5, the polynomial algorithm takes 13 minutes. Now what is 2 to the n? It takes 366 centuries, right? So this is extremely large. So the exponential growth was very, very fast. Well, the typical story about exponential growth is this chessboard. So there's a historical background from the textbook. So roughly says, probably it's in India or somewhere, there is a very clever guy who invented chess, right? So he introduced the chess to the king, and the king was very happy. So the king is asking, what should I give you in return as a reward? So the clever guy says, oh, you just put one grain of rice in the first square of the chessboard, and then 2 grains of rice in the second, then double amount in the third, and so on and so forth. So the king was saying this is very modest, right? So you just do it, and then, but it turns out, okay, so according to the calculation done in the textbook, so you need this number, the 2 to the 64, right? So here, look at n equals 60. So this is about that. So it's 2 to the 64 minus 1. This amount of grain of wheat or rice, whatever. So now what is the weight? So the weight is the tremendous amount of wheat. So this is about, more than 1,600 times of the global production of wheat in the modern times, right? So the Indian king has no way to produce that amount of reward to the smart guy. Right? Well, I don't want to guess what happened to the smart guy. Okay, so the message was exponential time. The growth was extremely fast. Don't be fooled by the first few terms. So when n gets bigger, it goes tremendously fast. Okay. Oh, I have to speed up, but we don't have much to. Okay, so the last few slides are talking about exponential. We already talked about exponential growth. So we talk some property about exponential function, and then we talk about log function, and then that's the end of the lecture. Okay, so what is the exponential function? So exponential function actually refers to a family of functions. So for example, 2 to the n, if you think n as input, 2 to the n as output, so this is an example of exponential function. Right? Just now the calculation about the chessboard are this exponential function, 2 to the n. So in general, you can change the 2, right? You don't need to have 2. So you can consider 10 to the n or pi to the n. So you can have others. In calculus, you can define a to the x, where x is a real number. So here, n is an integer. I can explain a to the n as n copy, as a product of n copy of a's. But if x is a real number, say x is pi, I cannot use product. I cannot say take pi many a and multiply together. But calculus tells you there is a way to do that. Okay. So in mathematics, exponential function can also mean this kind of function. You can take 2 variables. One is the base, the other one is the exponent, right? So you can think of them as a function of 2 variables, x and y, and the exponential function is x to the y. Okay. Very often we use e to the x, where e is a constant named after Euler. Right? Euler starts with e. Right? So this e comes from Euler. So the value of e is 2 times. Okay, it's this number. The number e actually is extremely important in mathematics, probably in engineering also. So the property of exponential function is if you multiply a to the x with a to the y, you just add up the exponent, right? And you raise the power consecutively, it becomes product. Okay, so I think you know this from JC. Also, if you know a little bit calculus, the nice thing about the e is if you differentiate e to the x, you still get e to the x. Now, exponential function is 1, 1. It's strictly increasing, so it has an inverse. Right? So the inverse is called log. Again, I think many of you know this. So for example, if 10 to the x is y, and then suppose you know y, you want to get x, the function, the inverse of exponential is denoted by log. Here the 10 is the base, so the log take base 10 log to y, you get back x. Right? You can also take base 2 log. For example, 32 is 2 to the 5, you take base 2 log. You get base 2 log of 32 is 5. Right? So the inverse of e to the x is called natural log. Right? So it denoted by this ln, natural log, which is the base is e. You take base e log. Okay. So the property of log function is the following. Log will turn product into sum. Log will turn the exponential into product. Okay. And also, in calculus, you know if you take derivative of log, you get 1 over x. Okay. Now, this is the last slide. So I want to explain the first fact, math fact. So there's a claim saying when x is small, log of 1 plus x is almost the same as x. So from there, we talk about the rule of 72 or something, right? So is there any evidence? Well, the numerically it's true. For example, look at this table. When x is half, this guy is 0.4. Well, not too close. But if you choose a small x, like x is 0.001, then log of 1 plus x is this number. It's very close to x. Right? So indeed, numerically, they give us some evidence. But mathematically, you can justify this by using, well, Taylor expansion. So log of x, you can expand in this way, right? You can expand this way. Now, when x is small, x squared is much smaller. Because if x is like this, x squared, you add 2 more zeros, right? So it becomes much smaller. So the older terms, so x is the only major term. All these guys become extremely small, can be ignored. So that's why the log of 1 plus x is more or less x, right? So that's this is the mathematical fact 0. Okay. So with this, we end the chapter of money and personal finance. So see you next week.